Hi, my name is Samyuktha, and in this video, we will be looking at Module 4 of Engineering Physics, which is called the Applications of Quantum Mechanics. In this module, we will look at the basics of nanophysics first, and then move on to quantum confinement and nanomaterials. After this, we will look at quantum tunneling, and then an application of quantum tunneling, which is the scanning tunneling microscope. What are nanomaterials? A nanomaterial is defined as a substance having a size of roughly 1 to 100 nanometers, or at least one dimension in the nanometer range. Now, the science at the nanoscale is special because at such a small scale, different laws dominate over those that are experienced in our everyday lives. A key feature of nanomaterials is that with the varying size, the properties also vary. This gives a high degree of controllability, which cannot be achieved in bulk materials. Now, nanomaterials can be designed for increased strength, chemical reactivity, and conductivity. Because of all of this, nanomaterials are revolutionizing the field of science and engineering. Some features of nanomaterials are the large fraction of surface atoms, which is also called the high surface area to volume ratio, high surface energy, spatial confinement, and reduced imperfections. Let us look at the property of surface area to volume ratio. As the material of the size reduces, the surface area to volume ratio increases. If this is a material, this is a bulk material. Now, if this material is made into a nanomaterial, then there will be lots of different cubes, and the total volume stays the same for these. But for each cube, the surface area is more as compared to only the surface area of the bulk material. The volume formula is 4 by 3 pi r cube, and the area formula is 4 pi r square. Now the ratio is A by B, which is equal to 3 by R. Because A by B is higher for nanoparticles, they are also more reactive. And here is the graph between A by B and R. It increases with decrease in size. Now let us look at quantum confinement. If we reduce the size of a material from the bulk size, then the electrons in the material, they get confined to the region of the size of the material. So in nanomaterials, the size of confinement is of the order 1 nanometer to 100 nanometer. At these confinement length scales, the electronic energy levels are not continuous, as in the bulk. So in bulk materials, they are continuous, but because of the confinement length scales, the electronic energy levels are not continuous and instead they are discrete. This is because of the confinement of the electronic wave function. So, in other words, we can give the definition of quantum confinement as the spatial confinement of electrons in one or more dimensions so that the energy levels are quantized. Let us talk about density of states. The density of states quantifies the number of different states or energy levels in the neighborhood of an energy level that the electrons are allowed to occupy. It is a measure of how closely the levels are to each other. The density of states, it depends on the dimensionality of the confinement. So it can be of 1D confinement, 2D confinement, and 3D confinement. Quantum confinement can occur when the grain size is comparable to the de Broglie wavelength of the charge carriers. And secondly, the grain size is comparable to Bohr's excitonic radius. Firstly, let us talk about 1D confinement. An example of this is quantum wells. And 1D confinement happens for two-dimensional materials. The electrons are confined in one direction and they are free to move in the other two directions. And due to the confinement in one direction, the energy shows the quantization effect. And the density of states, it remains constant for a range of energy and it increases suddenly by a discrete amount. And this happens over and over again with the increase in energy. Some examples are graphene and layered nanomaterials. Some other examples are and these are transitional metal dichalcogenides. Now, let us talk about 2D confinement, an example of which is a quantum wire. This happens for one-dimensional materials. In this, particles are confined in two dimensions and are free to move in only one direction. The energies are continuous in one dimension, that is, along the wire's length, because the particle's energy levels are continuous and they can vary smoothly because the particle isn't restricted in this direction. And they are discrete in the other two directions, meaning they can only take certain specific values of energy. Some examples are carbon nanotubes, and gold nanowires. Now, 3D confinement happens in quantum dots. And it happens for materials that have zero dimensions. The particles are confined in all three directions. And so that means that they cannot move freely in any spatial direction. This scenario is analogous to a particle confined in a 3D well. For example, in a tiny 3D box, a particle cannot move upwards, downwards, or out of the box. Now, the energy levels are completely discrete. This means that it can only have specific energy levels. These energy levels are not smooth or continuous. They are more like a staircase where the particle can only stand on certain steps. The density of states is a set of delta functions. This means that there are sharp, distinct points where energy levels exist, with nothing in between. Now, an example of this are gold nanoparticles. A gold nanoparticle is a small, tiny sphere of gold atoms. They are so small that the electrons inside are fully trapped. These are the graphs for 1D confinement, 2D confinement, and 3D confinement. Now, let us look at the effect of confinement on the energy levels. In a single atom, electrons are allowed to have only specific, discrete energy levels. These levels are far apart because they are determined by the quantum mechanics of just one atom. But for a collection of atoms, when the atoms come close together, like in a solid material, their energy levels begin to interact. The levels from different atoms mix and split into multiple closely packed energy states. Now this happens because the electrons in neighboring atoms feel each other's presence. So as the number of atoms increases, the number of these closely spaced energy states grows. So as the number of atoms increases, there are more closely spaced energy states. Therefore, when we increase the material size, the band gap decreases. And when we reduce the material size, the band gap increases. The larger band gap in nanomaterials significantly impacts their properties and behavior. So, a larger band gap means that the materials absorb and emit higher energy or shorter wavelength light. So, a large band gap means that they absorb or emit higher energy, and higher energy means shorter wavelength. An example is in quantum dots, the smaller particles emit blue or violet light, while the larger particles emits red or yellow light. This is used in LEDs, lasers, and other display technologies. Another example is cadmium selenide, in which, when the size is 5 nanometers, they are red in color, while if the size is 1.5 nanometers, they are violet in color. Here are some of the applications of quantum dots. They are used in solar cells, lasers, biosensors and bioimaging, flat panel displays, memory elements, and in photodetectors. Let us talk about some other properties of nanomaterials. Firstly, chemical properties. The percentage of surface atoms in nanomaterials is large compared to bulk objects. So the reactivities of nanomaterials are larger compared to bulk materials. Secondly, thermal properties. The number of atoms in the surface is larger compared to the interior. This is due to the surface area to volume ratio in both these cases, and so because of this, the melting point is lower. So for nanomaterials, the melting temperature reduces with size. Thirdly, optical properties. The change due to quantum confinement effects. Now, magnetic properties. Non-ferromagnetic bulk materials show ferromagnetic properties when they are reduced to nano size. To understand the concept of quantum tunneling, let us examine a quantum particle which encounters a barrier. We already know that particles will reside in regions of lower potential. For example, objects fall to a lower gravitational potential, and uncharged particles move from regions of higher potential to lower electric potential. Similar to this, we can imagine that a particle is traveling in this region where the potential equals 0 and it possesses an energy of 0.5. After this, it encounters the barrier which has a potential equal to 1. So, according to classical physics, we can conclude that this particle won't be able to surpass the barrier because it doesn't have enough energy to do so. For example, if it had above an energy of 1, for example 2, then it would be able to go above the barrier. It will completely miss the barrier and go above. But since it only has 0.5, technically the particle shouldn't be able to cross the barrier. Since this is a quantum particle though, it will behave much differently because they have both particle and wave-like nature. Let this point be 0 and let this point be A. Now we are considering a singular finite energy barrier. We can refer to this as V0. Now V of x equals to V0 when x is between 0 and A, and when x is less than 0, V of x will be equal to 0, and when x is greater than A, V of x will also be equal to 0. In this graph, the vertical represents energy. So we can see that the energy of the particle will determine whether it will encounter the barrier. If the particle has an energy that is much greater than V0, then it will not encounter the barrier. If it has an energy that is much smaller than V0, then it will encounter the barrier. Now we will write the time independent Schrodinger equation. Let us name these regions A, B, and C. In regions A and C, V of x is equal to 0. So for these two regions, this equation will change and we will make this into 0. In region A, after changing that term to 0, we will get after this, if we multiply both sides by minus 2m by h bar square, multiplying on both sides, we will end up with this equation. And this will be 1 because we're talking about region A. We know that k is equal to root of 2me by h bar square. So we replace this by k and it becomes now we write the solution for the second order differential equation. Psi a of x is equal to a e power I k ax plus b e power minus I k ax. And this is along the positive x direction. This is along the negative x direction. We can see that the conditions for region C are very similar to the conditions for region A. We can also write the solution for region C. Psi c of x is equal to e into e power I k c x plus f into e power minus I k c x. And this is along the positive x. This is along negative x. Now we have the solutions for region C and region A, but not for region B. For region B, it is a bit more complicated because for region A and C, the particle was free to move, but for region B, the particle is not free to move. So we cannot make this 0 like we did for A and C. For region B, we can replace V with V0 because this is the potential of the barrier. Now for region B, we can't use the same types of functions that we used for region C and region A where the potential was 0. These functions are complex exponentials. Now we need to use real exponentials. This is because complex exponential functions describe the behavior of a wave that is stationary and unaltered by a potential. In contrast, localized functions or real exponential functions, they represent a wave that occupies only a narrow domain and then stops abruptly. This is what we will use for wave functions in the region B because it is a mathematical representation of a barrier. So here we will not use this I complex. Now to simplify this, let us first subtract this term from both sides and it will become we can combine these two terms and write it like this. Equal to 0. Now we can multiply 2m by h bar square in both sides of the equation. For regions A and B, it was minus 2m by h bar square, but now it's positive 2m by h bar square. Doing that will result in this equation. And now we can get the value of Kb as root over 2m V0 minus E by h bar. So we can replace the above equation by Kb square is equal to 0. Now we have another second order differential equation. Now this equation is for when E is less than V0. When E is greater than V0, we can write another equation which will be like this. And the value of K B, but this will be above the potential barrier. This value will be now this is the equation for when E is less than V0 and this will be the equation for when E is greater than V0. For this, we can use a function with complex exponentials because it is above the barrier region. But for this, we need to use a function with real exponentials because it is inside the barrier region. So we can write the solution like this. And for this, These are the solutions. After splitting the functions that we got for a, b and c, we get these set of functions, and now we can consider a particle moving in this direction. So immediately the same particle cannot be moving in this direction, so this cannot be considered. But everywhere else the particle can be moving. For example, it can move here, here, and here. It can even reflect back after hitting the barrier, so this is also possible. And it can move through this or also reflect back after moving some distance inside the barrier. So this is also possible. But this is not possible because the particle is not moving from this direction. The function of psi c of x becomes e into e power I into kc x. And for psi of b1, this was the function, but this is not physically acceptable, and so it becomes this, d e power minus k b1x. Now, mod of psi square is the probability density, and so in this way we can get the incident flux. We now end up with a diagram like this, where psi a of x is equal to this function, psi b of x is equal to this function, and psi c of x is equal to this function. Now we can find the reflection probability and transmitted probability. Here b is the coefficient for the reflected wave and a is the coefficient for the incident wave. So we can find mod of b square by mod of a square as the probability for reflection, and similarly for transmitted probability, E is the coefficient for the transmitted wave. And again A is for the incident one. So mod of E square by mod of A square is the probability for the transmitted wave. Adding the reflection probability and the transmitted probability will give us 1. Now we can also find the tunneling probability. We know that psi b of x is continuous, and so to find this we take psi b of 0 and psi b of a. Here when x is equal to a and x is equal to 0. So mod of this function square by mod of this function square. We already know that psi b of x is d e power minus kbx. And here when x is substituted as a for the numerator, we get e power minus 2 kba when multiplying. And below, x will be substituted to 0. So e power 0 into e power 0 will be equal to 1 into 1, which is just 1. That is why 1 is written over here. And in the end, we get mod of d square by mod of d square, which cancels off, and this will be the final result. So the tunneling probability is equal to e power minus 2 kb into a, where a is the length, and kb is equal to root over 2m by v naught minus e by h bar square. Now let us talk about a scanning tunneling microscope, which uses the principle of quantum mechanical tunneling. It was invented in 1981 by Gerd, Binning, and Heinrich Roer, and it was awarded the Nobel Prize in Physics after 5 years. The scanning tunneling microscope consists of an electrically conducting probe with a very sharp edge, and it is brought near the surface of a material to study the material. This tip is usually made up of pure metals or alloys. and there's a gap between the tip and the surface, and this represents the barrier. The tip and the surface are the tip and the surface are the two walls of the potential well. Here is another diagram of the scanning tunneling microscope. This is a piezoelectric tube with electrodes. A piezoelectric is a crystal that creates potential differences when mechanical stresses are imposed on it, or vice versa. This is the tunneling voltage, and the tip surface separation is controlled to be constant by keeping the tunneling voltage at a constant value. This is a tunneling current amplifier. When we raster the tip across the surface, we get a current and use that current as a feedback signal. When this tip is brought about 1 nanometer of the sample, electrons from the sample will begin to tunnel through this 1 nanometer gap into the conducting tip, or vice versa. And this is what creates the current, which gets amplified by the tunneling current amplifier. And this is a distance control and scanning unit. And from this, the data is processed and we get a display. The applications of a scanning tunneling microscope are that they are used in industries and fundamental research to obtain atomic scale images of metal surfaces. And it is also used to provide a 3D profile of the surface, and doing this is useful in characterizing the surface roughness and observing surface defects. We can also study the surface and structure of organic molecules. And for tunneling to actually occur, both the sample and the tip has to be a conductor or a semiconductor, which is why we use pure metals or alloys like this for the tip. So scanning tunneling microscopes cannot be used for imaging insulating materials. With this, we come to the end of this topic. Thank you for watching.